In this video, I want to talk about one of the examples that we discussed in class concerning the chi-square test and how the chi-square test is used to determine if a predicted proportion is indeed correct. The question concerns one of Mendel's pea plant experiments. Mendel did an experiment trying to determine the genotypes of his pea plants, and for using techniques that we're not going to discuss in our statistics class, we found that there were 38 pea plants that had this genotype, where capital Y is the allele denoting yellow, little y is the allele denoting green, capital R is the allele for round, and little r is the allele for wrinkled. So Mendel believed that 38 of the offspring had this genotype, 60 offspring had this genotype, and so on, for a total of 529 offspring that he was able to successfully genotype. The question is, does it appear that these 529 offspring follow the laws of genetics that were discovered by Mendel? And the law of genetics states that the genotype should follow this proportion. This is a fancy way of succinctly writing down 9 different fractions. So if we add up these 9 numbers, 1 plus 2 plus 1 plus 2 plus 4 plus 2 plus 1 plus 2 plus 1, we get 16. So writing these numbers like this is a succinct way of writing out the 9 different fractions: 1/16th, 2/16th, 1/16th, and so on for all of the fractions. So according to Mendel's laws, what would be expected here would be, well, there are 529 total offspring, and then 1/16th of them should have been in this genotype for a prediction of 33.0625. That same expected number would fall here, here, and here. All of those are the ones in the proportions. 2/16ths would be predicted here, so 529 times 2/16ths would be the expected number for that class. That same prediction would go here, here, and here. And finally, 529 times 4/16ths would be the prediction for the class in the middle. Okay, as you can see, the observed are reasonably close to the expecteds, and basically the question is, are they close enough? The chi-square test is used to determine this. Using the chi-square test, the null hypothesis is always that the predicted ratios do work, while the alternative hypothesis is that the prediction does not work. So the alternative hypothesis is very modest when using the chi-square test. Okay, now to perform the chi-square test, we assume the null hypothesis and kind of work through the logical ramifications of making that assumption. To begin, we find all of the differences of the observeds minus the expecteds. And that's, so I take 38 minus 33.0625. I can do that in Excel with the spreadsheet fairly quickly and then fill down to get the other 8 categories. If you are not using Excel, then of course this can be done with a calculator by just simply doing all the differences. The chi-squared statistic is a way of combining all 9 of these differences into a single number. And the way that we do that is given by the formula down here. Chi-squared is equal to the observed minus the expected squared divided by the expecteds, and then adding them all up. So for example, this category here, the contribution would be the difference squared divided by the expected number. And so we get, in this case, 0.737. And we do this for all 9 categories using the fill down feature. Makes it a little bit quicker to get. And again, if you are using a calculator as opposed to Excel, then it's not conceptually hard. You just have to take the time to compute all those numbers with your calculator. So adding up these 9 numbers, we get our chi-squared statistic of 2.81. So that is the test statistic that we have for this experiment. Now the question is that large enough to decide to retain or reject the null hypothesis? As we discussed in class, this number will be large if at least one observed is a lot different than one expected. So if one of these categories is significantly different, they would have a large number over here, and that would give me a large sum. On the flip side, if all of the observeds are decently close to all of the expecteds, then all of these 9 terms would be decently small for a reasonably small sum. So In conclusion, a large value of chi-squared would be evidence against the null hypothesis, that at least one of the observeds is quite a bit different than one of the expecteds. However, a small value of chi-squared, or at least a relatively small value of chi-squared, would be evidence for the null hypothesis. There are two ways to determine whether to retain or reject the null hypothesis. The first way to decide this is by computing the p-value. And the p-value is computed in Microsoft Excel is by chi-square.dist.rt, this one right here. As you can see on screen, it returns the right-tailed probability, and it probably leaks off the screen, for the chi-squared distribution. So if I use this command, chi-square.dist.rt, the value of x is 2.810961, and in my case I've got 8 degrees of freedom. The number of degrees of freedom will be the number of categories minus 1. So in this case there are 9 different categories, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the number of degrees of freedom that I use will be the number of categories minus 1. So chi-square.dist.rt would be equal to 0.946, a fairly large p-value. This can also be, that's using Microsoft Excel, and so that's the command in Excel 2000. So let me copy that. Well, let me just show the command again. We have sq.dist.rt parentheses E198. If you don't have Microsoft Excel, but instead have Microsoft Excel 2007 or before, there's also a command chi-dist. That's the way it used to be in the old days, in Excel 2007 before. And this command does the exact same thing. Chi-dist E198. This will return the exact same number as what we just saw, 0.94565. So if you don't have Excel 2010 but have a prior version of Excel, then this other command is the way it used to be. And if you have Excel 2010, of course, you're welcome to use this as well, because this is included as to provide backward compatibility with old versions of Excel. If you're using a calculator, let me pull up the calculator so that I can show you how to do that over there with the calculator. So if you're using a calculator, the command would be, well, at least for the TI-83, let me move this over here. On the TI-83, it'd be second distribution, and there is a option, chi-squared CDF, which I choose. I choose CDF, not PDF. And the arguments for this one, I need actually 3 arguments as opposed to 2 arguments. So in Excel, you'll see I need 2 arguments, and the calculator needs 3 arguments. For the calculator, it would be 2.810961. And then I input in a right endpoint. Now, the right endpoint that I'd like to input is infinity, but I can't do that, so let me put in some big number that is essentially infinity, so that I have something to at least cut off. And finally, the last endpoint is, the last argument is the number of degrees of freedom, 8. So for the TI-83 plus, the chi-squared CDF, left endpoint, right endpoint, 8, and that will return the same area, 0.94565. What does this number mean? Well, in the picture, if I were to have, here's my x-axis, here's the y-axis and x-axis, and I have a chi-squared distribution with 8 degrees of freedom, the total area under the curve is 1. If I draw 2.81, that's going to be about here someplace. And the meaning of the chi-square distribution is that if I find this area out here to the right, then this area would be what we just computed, 0.9456, something that's less than 1. Okay, so one way of concluding would be that this p-value is larger than alpha. 0.945 is significantly larger than 0.05, and so we choose to retain the null hypothesis. Here's a second way of getting to the exact same conclusion. So here was my mark so there's my mark 2.81. A second equivalent way of figuring out whether to retain or reject the null hypothesis is to figure out what is the critical value. What is the value of critical value chi-squared critical so that the area to the right is 5%? So that's another equivalent way of getting at whether or not to retain or reject the null hypothesis. So the p-value is this. We can also compute the critical value. To get the critical value, the command is going to be chi, and you see down here, chi-squared inverse RT. That returns the inverse of the right tail probability. In other words, I put the area that I want, and the thing that returns is the x-coordinate that matches the area. So this will be the critical value. I input the area, and an x-coordinate comes out, and the critical value turns out to be 15.5073. In the picture, what that means is, is that for this area, this chi-squared value is roughly 15. Let me put in a couple more decimal points. 15.5073. So 15.5073. So let me just round off 15.51 for the sake of the picture. And so what I have is the following. If this number is over here, so this area is 5%, which means the area to the right of 2.81 has got to be something bigger than 5%. Whatever it is. In fact, if this number was anywhere to the left of 15.51, so if I were here, say, the area to the right of where the cursor is right now has to be bigger than something than 5%. So that means that if I'm over here anywhere, I will choose to retain the null hypothesis. I fail to reject, because the area to the right of any mark over here would have to be bigger than 5%. On the flip side, if it was over here, I would choose to reject the null hypothesis. Because if the mark was, say, here, where my cursor is, then the area to the right of the cursor would necessarily be less than 5%. So this provides a way of determining whether to retain or reject the null hypothesis based on the x-coordinate as opposed to based on the area. So there are two ways to decide to retain or reject the null hypothesis. You can compare the two areas. So compare the area here, 90.94 versus 0.05, or you can compare x-coordinates, 2.81 versus 15.51. So there's the critical value. That number is bigger than 2.81. So either way, either by comparing the p-value to alpha or by comparing the critical value to the value of chi-squared, we come to the same conclusion, is that, and let me fix the formatting here, we fail to reject the null hypothesis. It appears that Mendel's laws are correct. And let me fix that so we can see that better. So that is the procedure for doing the chi-square test for determining whether or not a proportion is correct. Let me point out that on the TI-83 calculator, to my knowledge, it is not possible to directly get the critical value. The TI calculator will figure out the p-value, but not necessarily the critical value. In order to get the critical value, you could look at the charts that are given in the textbook and figure out the critical value by reading the chart. So that just looking at 8 degrees of freedom and choosing alpha to be 0.05 and then getting that number directly. So that number can be obtained off the chart even if your calculator does not return that value.